Hello, everyone, and welcome. My name is Cristian Hernandez-Blick, head of program at Interspecies Internet. It's my pleasure to welcome all of you on behalf of the trustees in the organization to another Interspecies Conversations lecture. Interspecies Conversations is a monthly online lecture series where leading thinkers share ideas and research that deepens our understanding of communication and cognition in other species. We aim to platform emerging discoveries and host open discussions where the community can join the conversation with questions and feedback. So if you enjoy today's talk, please consider donating to Interspecies Internet to help support our programming and other projects and activities. You can find a link to our donation page on our website, interspecies.io, as well as in the video descriptions on our YouTube channel. And Caro may share the URL in the chat with you as well. Yeah, so today we're very excited to host Gašper Beguš, who will be presenting on machine learning, sperm whale communication, ethics, and law in his talk, Finding New Patterns in Animal Communication with AI, Ethical and Legal Implications. Sperm whale vocalizations rank among the animal kingdom's most intriguing communication systems. Until now, their click clusters, otherwise known as Codas, were treated as a Morse code-like repertoire. Using explainable deep learning techniques, Dr. Beguš will present acoustic evidence that Codas function as vowel-like units. They have structured and discretely distributed formants, display systematic duration contrasts and distributional patterns, and participate in co-articulation. These properties reveal a strikingly structured combinatorial phonology that parallels human language more closely than most other non-human systems described to date. This discovery extends beyond biology. Beguš will examine how detecting human-like linguistic structures in whales challenges prevailing assumptions about non-human communicative competence and their legal status. He'll further discuss how the linguistic behavior of non-humans helps us understand the relationship between language, intelligence, and thought. By integrating interpretable AI with linguistic theory and law, this work situates sperm whale communication at the forefront of language research and reframes the conversation on the philosophical, ethical, and legal status of human and non-human communication. Gašper Beguš is an associate professor at the University of California, Berkeley, where he bridges the fields of linguistics, artificial intelligence, and cognitive science. His research centers on interpretable AI and the study of language in humans, animals, and machines. Dr. Beguš leads efforts to develop techniques that help us better understand the inner workings of AI. In his Berkeley Speech and Computation Lab, he also builds the most realistic models of human language learning, creating an artificial baby language learner. Serving as the linguistics lead at Project CETI, a nonprofit dedicated to listening to sperm whales, he researches one of the most intriguing communication systems in the animal kingdom. His recent research discovered that sperm whales have equivalents to human vowels. So Gašper, we're so happy you could be with us today, and whenever you're ready, the floor is yours.
Thank you so much. I really appreciate this wonderful introduction, and thanks everyone for joining today on this fine Saturday. Thanks so much to the Interspecies Internet for providing this platform and for inviting me today here. Such a wonderful community of people who are interested in language of animals and human language as well. So thanks so much for that. And so today I want to kind of talk about a couple of big topics. One is a discovery. How do we make discovery in animal communications? And we know that this has been pretty difficult in the age of quantum mechanics and highly complex scientific discoveries. We are still, in a sense, pretty early when it comes to decoding animal communication. We are still at the I would say the beginnings, and still oftentimes not so skillful at that. And the reason I think is because animal communication is so complex, and we have human biases. And so how do we get across those human biases with the help of AI? And then what does that mean for the ethical and legal status of the animals? And so I want to bring together a couple of seemingly different topics, diverse topics, into a story where I'm going to show you how we approach this problem, what we found out, and what we think that means for the legal implications. So, what is language? It's a very complex question. I'm a linguist. I should know this, but I actually don't. So, when people ask me what is language, I try to say, well, we don't know. It's better than, asking what is language or like, do animals have language? To try to understand what the properties of language are, and then what animals have and what they don't. But the good definition of language, as with any definition, it's still lacking. Um, what is uniquely human about language is something that I think is more achievable to answer that question. And how it evolved, I think understanding animals and being really open to other communication systems when one studies language is super important. Traditionally, of course, linguistics has been has had this position that human language is something uniquely human, and that there are mechanisms, regardless of what do you think the mechanisms are, but there are mechanisms that make our language very different from animal communication systems. So the Chomskyan tradition is very explicit, saying that there's discontinuity. So the animal communication is very different from human language, and they have certain properties like merge or some logical operations. In terms of evolution, it has been thought that language is actually develops based on a genetic mutation. So that's one worldview, one mindset that existed before. And then the other is, of course, a different position, which is language as a continuum, right? So language as a result of the general expansion of human cognitive capacity, right? So the idea is that there is no discontinuity between us and animals. Basically, we just have different communication protocols, right? So language as a communication protocol where I have some internal state and I use that protocol to communicate my internal state to my conspecifics, and communication happens, and that channel is language, and it is dissociated from complex thought. And evolutionary, there's continuum between human language and animal communication system. Of course, no animals have exactly the same language as we do, but they have traces, they have aspects of language. And in different species, different combinations of abilities come together, and we have human language, other animals have other languages or other communication systems. So these are basically two very different worldviews, and I'm going to talk today about how using AI we can understand these animals better and try to understand these two very complex questions: what is language and how it evolved, and of course, what is uniquely human about our language. Several people on this call, I'm very honored to have them, that have shown, or in the history or in the past, that animals have many aspects of human communication systems: symbolic computation, semantic form meaning pairs, complex learned vocalizations, dialects, basic structure, basic compositionality. Many aspects of language have already been discovered in non-humans. And so I'm part of Project SETI, which is this wonderful scientific community um, comprised of very diverse people, from machine learning scholars to linguists to biologists, and we're interested in sperm whales. And I'm going to talk about the sperm whale communication system today. So on the surface, they have this very intriguing click-based communication system. Unlike dolphins, they don't whistle, they only have these clicks. They put clicks into groups of clicks that they exchange. They're called codas. And the first time you look at this, the first time you know are faced with sperm whale communication system, it looks nothing like human language. It sounds more like alien than human language. But when you look at it very closely, when you use when you can step outside your human biases, you can see really distinct parallels, and really strong parallels. They're very structured. And I'm interested in all sorts of linguistic representations, from syntax, phonology, and I'm going to show you step by step how, you know, every time we look in this communication system, the more parallels we see with actual human communication system. And then what does that mean for the legal status or the rights of these animals? Because we've been doing a lot of work on showing, and the community has done a lot of work on showing that language-like elements are present in animals, but we haven't really thought about very carefully, thoroughly, what does that mean for the legal status? What does that mean for the legal personhood status? So what part of the talk, at the end of the talk, I'm gonna open these very important questions, like if we find these human properties in non-humans, what does that mean for the legal status? And with the help of AI, we basically discovered something that is really quite unique, namely the spectral structure, that spectrum has potentially meaningful characteristics. So that spectrum is highly structured, something that looks very similar to human vowels. And I'm going to give you a story of how we get there. But first, what is language? We don't know what it is, but I can give you a few ideas of how we communicate, right? So I have some information in the brain. Let's say that information represents a red apple. I have learned to move muscles in such a way that the sound that I produce by moving my mouth and tongue, the sound that movements produce carries information, travels to your ears membranes vibrate, those vibrations get transformed into electric signal, and your brain needs to take this completely physical property, which is sound, measurable physical property, and turn it back into information, right? So I have some information, you have information now. If your information is red apple and my information is red apple, we have successfully communicated. So what we do in as part of this project and part of my lab's project is we're building alternatives to large language models. Okay, so large language models are great for many purposes, but they're not very good at mimicking how humans and human babies learn language. So what we do is we try to build an alternative to GPT that learns language just by listening to sounds with no engineering tricks. Just we're trying to build a model of human brain when a child is immersed into spoken language and it needs to learn that words, for example, that some sounds carry meaning. Now, this is, I think we underappreciate just how difficult this process is. Imagine a child, it is faced in a sense with an alien language, right? So the child, human language is, of course, we hear the correct frequencies, but it's a system that is very foreign to them, and they need to learn them in such a way that their vocalizations will look like parents' vocalizations, right, or caregivers, and will carry meaning, right? So when a child is born, it tries to imitate and imitate informatively. So we are building such a model with AI, but like it's an alternative to LLM. Our models don't get any text. They don't get massive amounts of Wikipedia articles. They get words in raw sound, and they need to learn this very difficult task, which every child is faced with, from this physical property of sounds, learn words that carry meaning. So we're building this model that basically treats language as informative imitation, right? You can define language in many ways. I like to define it by necessity as informative imitation, right? You're faced with some communication system of your environment, and you need to learn to encode information into the channel. And we have a model that looks a little bit like this. We won't go into the detail about modeling, but it's a GAN-based model where a network produces sounds, another network forces that network to imitate, and then a third network learns to decode sound. So it's like production and perception. Basically, they're like very completely unsupervised modules that internally need to, on their own, come up with words and learn things about language. And so they learn by imitation, crucially. They learn by imagination, and they're very innovative. So those are all good I mean, if you describe a human child learner, they're very imitative, they're very imaginative, and they create new words, they're very innovative. This is how the model looks like in all its details, the latest instantiation of that. And the point is that this is a more realistic, unsupervised approximation to how humans actually need to learn language. Then we can use this model, basically, to look inside and see what did this model learn about human language, right? You take this artificial model, you mimic human baby language learner, you just give it some sound and ask about language did this model learn? And we're getting something that a lot of AI models are striving for, but many models are not achieving, which is the model learns to encode each concept or each word or each sound in language as a single neuron. And this in neuroscience is called monosemanticity. And the idea is that the model basically takes a physical property of sounds and learns to represent them in a symbolic way. And that's very important because we think that humans are symbolic, our language is a symbolic system, and we think that many animals can do symbolic communication. And so we are able to show with these models in several papers that the model encodes meaningful concepts about language with a single neuron. So monosemanticity arises in a fully unsupervised way in this model, which is great. For example, the model learns the model is trained on 8 words, and it learns to encode, or it learns every word with a single neuron in this deepest layer of its representation. So it's as if you took our brain and you were able to pinpoint to a single neuron where the word, I don't know, start is encoded. Now, we don't know if this is exactly how the brain works, and some people, there are like differences of opinion on that. But we have shown that our models are also very similar in the way that process sound. This is a different research program, but these are good approximations of a human that needs to learn. The model also creates new words. So that was a nice discovery when we were training these artificial models. We trained it on 8 words, and the model learned all the 8 words, but it also started saying new words. So it was trained on this 8 words.
Carry dark, greasy like suit, water, year.
Start. And it says start, although it never heard start before. And it says dust. So based only on 8 words, he was able to create new English words that could be part of English word vocabulary. We have this other paper, if you're interested, where we show that these models are very good for modeling language evolution because the models, because they're innovative and because they're very productive, they start putting words together. They were trained only on single words, yes, they're started combining them. And this is extremely interesting now that we're observing more and more studies of animals showing that combinatorial calls have compositionality or traces of incompositionality, we saw something very similar in this paper. We show that the models start on their own to basically put words together, concatenate them, and not only concatenate them, not just throw them together, but also do that semi-compositionality. They're really nice traces of a compositionality, and we can pinpoint to a neural mechanism of how this happens. We call this inhibition. The point is we have this simulation now of how animals and human babies need to step from a single call system where one call has one meaning into combinatorial syntactic system where calls can be concatenated and then a meaning can be compositionality derived from those calls. So what we did, well, I think one of the powerful approaches to access animal communication and to get out of our human biases and into animals is to use these models or AI models, and instead of ask them to learn human language, ask them to learn any language. So we're building with modeling language, we're basically building an all-purpose pattern discovers. And because we can look inside and say, okay, this neuron encodes one word, this neuron encodes another word, we can basically use it to interpret what the model had learned about non-human language, right? So the idea is you take this artificial baby language learner, instead of language, you train it on some non-language communication system, non-human communication system, and see what are those neurons, what did those neurons learn about this communication system. So that's what we did. You can think of sperm whales communication system as decoding and encoding problem, right? Just like I had to encode the red apple, move my um, um, articulators so that you hear the sound that carries information about a red apple. Presumably, sperm whales do the same. They have some information, they encode it into these clicks and codas, and then they decode it. And that's how we treat their communication system for the modeling. And this is an example of the research that SETI is doing. Through a collaborative robotics team, we have gentle tags, minimally invasive, that are placed on the whale, and we record at the whales. Here are two exchanging codas and swimming toward the third whale. And so presumably, because this is before diving, before socializing, while socializing, presumably there is, in addition to social meaning, which there's a time we know they have dialects, presumably there's some referential meaning as well, but we don't really know the full extent of how they encode things into this communication system. So for the longest, it was thought that this is some sort of a Morse code type of system where the number of clicks and the timing between them. So click, 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 click versus click, 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 click. That's the thing that distinguishes the types, and they exchange those types. But when we train our artificial language learner, it suggested that there's more to it. So traditionally, number of clicks, several coda types, timing between clicks. It was so important to have tag data. So having recordings from the whale, it really helps because ocean is acoustically a messy place, and things can happen. Distorted signal is is very common, and so having that tag was very important. But also getting outside of our human biases was important. So what we did is we trained this artificial little whale learning codas, and we took that single neuron idea, like let's see what those single neurons actually encode, and we have this protocol. This is actually an archive called CDEV, which is causal disentanglement with extreme values, which is just a long word for saying we're taking and observing causally what each neuron is encoding. And our model predicted that number of, it used one neuron to encode number of clicks. It used another neuron to encode timing. And so this is good because it confirms that it found those things that linguists, people in biologists thought were important. But it also used spectral means and acoustic regularity. So it also used the spectral property to exchange meaning. So you have this artificial model that needs to take whale codas and needs to mimic them in a completely unsupervised way, needs to learn to imitate whalish in a sense, and do so informatively, right? I remember I talked about informative imitation. It learns to imitate, it learns to transmit information through codas, and then we can look inside it with our interpretability technique and see which neuron did encode what. And that is the approach that we were taking here that was very successful, because it predicted something we didn't know is meaningful, we didn't know existed as an important property, which is the whole spectral properties. Now, it didn't mean that, that's it. The AI model discovered everything, but it forced us to really dig deeply into the spectrum, right? So spectral properties of clicks were generally not looked at very carefully before. And then we went and really checked and found this thing that we called coda vowels, because they're so similar to human vowels. I mean, on the surface, they couldn't be more different, right? Clicks and vowels. I mean, like, you would think, what is this person talking about? But if you look very closely, you see very clear parallels. And we have another preprint that I'm gonna talk about where we even show that they actually behave similarly. So what are human vowels? We vibrate our vocal folds, and those produce the source of vibration. And then we change, when you see me speaking, I'm doing a lot of back and forth with my mouth, right? It's a very fast process. Our human speech is very fast. And so when I say an ah, what happens?
E.
This is me saying ah and e. You see these bands of frequency form. This is waveform, this is spectrograms, right? So you see these bands of frequency, the shaded parts, these are called formants, and they are resonant frequencies of the chambers that get created in my mouth when I speak, right? When I speak ah, I create this long, wide chamber. When I say an E, I put my tongue farther up and the chamber is more narrow, and there are two actually chambers that happen, and they have resonant frequency. Basically, I create these tiny tubes in my mouth, and those tubes result in resonant frequency. And it's similar to a church organ, right? You have larger or shorter tubes, and those will have different resonant frequency. Our vowels operate in a similar way. Again, if you look at the clicks, they couldn't be more different. But still, our AI model was suggesting, well, spectrum is important. The model used spectrum to transmit information. So we thought there may be something behind the spectrum. Let's dig deeply. And it took a lot of digging. But when we dig deeply enough, we found that when you actually start removing timing from those clicks, they start looking much more similar to human vocalic pulses. So when I said my vocal folds are vibrating when I say a vowel, when you start putting these things together, they start looking like human vocalic pulses, and the spectral properties start appearing that are very, very close to human vowels, right? And so this is how we realize, well, look, we have codas, that's groups of clicks. And some codas have two resonant frequencies or formants, or these bars, shaded bars, and some codas have one. And the really intriguing and interesting thing is that it's completely discretely distributed. If you're a coda, it's not some like continuous distribution. It's not some, some clustering that we were able to get. It's just like clear cut. You're either one type or the other. And you can even hear it with your naked ear, right? So the first click, the first this is Coda. This is Codas removed, timing removed from Codas. And if you listen to them, first type, second type, you can hear it with your naked ear. And if you actually put a lot of the entire conversation together, it'll sound something like this. You can see the quiet back and forth. So what was considered before just a repetition of the exact same coda type, these are all 1 + 1 + 3 codas. We see that spectrum is highly structured, highly and not repetitive, right? They're exchanging these coda types, and it's very, very parallel to human vowels. And this happens across whales. We have several whales now. We have also other recordings. We're working on other populations, whales in Galapagos. In all of them, you see this very discretely distributed. This really seems controlled and non-automatic. So across whales, repetitive patterns, and this is why we call these properties coda vowels, because they're so parallel to human vowels. We also found coda diphthongs, which is these A-type, one spectral peak type vowels that have very clear trajectory, right? So you see these beautiful patterns of trajectory going up and down. So some codas are very flat, but some have this up and down trajectory. Or, for example, you see in some codas, the first click is higher and the rest is level. So we observe all these patterns that, in functional terms, look very similar to human diphthongs like ow and I, where we combine, where we have this basically trajectory of the spectrum. And it's also repetitive across whales. We have several whales that are producing these same sets of vocalizations, the same set of spectral patterns. And we have another way to represent these. And actually, we were able to even find a way to, in raw form, represent codas, right? And you see that some codas have one formant, some codas have two, like this last 5 of them. And they also have differences in the way the clicks are distributed. And so this is all nearly parallel to human vocalic systems. So humans have tones, and the tones are achieved by different vocal fold vibrations. And so here tones would be achieved with different timing between clicks. And then on top of that, we have these chambers, resonant frequencies that are reflected in the spectrum that both humans and whales use. Probably, I mean, we know that we use them to encode information, but it looks on surface that whales are using them to encode information as well. So, the click can now be conceived as a vocal fold pulse. And then on top of that, the spectrum is achieved as a resonant frequency of some resonant body. And we were very happy to discover that, when we were doing, when we found out these spectral properties, it was like, what's the source? How do they do these? And if you look at the way the sperm whales produce sounds, and I think this is very interesting for a lot of cetacean researchers here, because sperm whales have only clicks, but nevertheless they have phonic lips. And these phonic lips in essence are the same as our vocal folds or vocal cords. And then on top of those phonic lips, they have an air sac. And the air sac acts as a resonant body in a very similar way as our vocal tract acts as a resonant body. And we did all the math, and actually checks out really nicely. If you think of this distal air sac as a resonant body based on the speed of sound in air, you can show that the first resonant frequency will be expected right at the rough, approximately the size of the air sac. And you can do some speculatory articulatory work as well, although articulation on sperm whales is extremely difficult to research. Now, I've shown you all the kind of acoustic phonetic properties of those clicks that look like human vowels. But we have another preprint. We're actually showing that not only do these vowels look like vowels, the coda vowels, but they also behave like ones. And so we show that some coda types, traditional coda types, have roughly half A type vowel and half I type vowel. So we call the vowels with the single formant the A vowel, and the vowels with two formants the I vowel. And then some codas have only A vowel. And so that's a distributional pattern that exists in human, for example, in my language Slovenian, some vowels don't like some specific rates of vibration. So this is an exact parallel to this distributional pattern. So we see distributional patterns of these coda vowels. We see durational patterns. For example, human vowels, some vowels like ah is intrinsically longer than others. Whenever you say an ah in English, so when you say a word ba versus a word bi, the I is slightly longer, even though you might not hear it, but it is, trust me, slightly longer. And we saw similar durational patterns. And we saw that some coda vowels, that the I vowel can have a short and a long version. And we know that human vowels have short and long, some like Latin, for those of you who learned Latin, or Arabic, you have long vowels and you have short vowels. And that's how humans transmit information. Now, again, we're basically investigating the property, the basically properties of this communication system. We're trying to figure out how this works. We don't know, we're making progress on the meaning of this, but we don't have referential meaning yet. But from the structural perspective, this now is an extremely rich, complex, structured, combinatorial communication system. And you know, on the surface it looks like a Morse code, but when you really dig into their communication system, you see just how parallel it is. We also shown that there are like baseline differences between whales that are similar to baseline speaker differences in humans. Co-articulation is something that they have as well. And so all of this was basically discovered because AI predicted that spectral properties are potentially meaningful in this communication system. And we were able to confirm this with analytical tool. But of course, the human in the loop is still necessary. It's not the case that AI is making all this discoveries just by, you know, me typing in into a chatbot, find something new about sperm whales. It's like you use it as a tool with the interpretability to kind of get outside our human biases. Because in a sense, what my human bias was that our vowels are very fast, right? When you saw that vibration, it happens with a very high frequency, and these animals, you just need to remove timing. You just need to make their communication or their vocalizations faster, and you see all these patterns. And so AI can help you to get outside of these biases and outside of looking only at what is meaningful to us. And that can really accelerate insights. And hopefully that kind of approach where you're basically building a model and then testing it on human first, transferring it to non-humans, and then using AI interpretability techniques should be useful to basically in principle, any language animal communication system. It doesn't have to be sperm whales. And we have all the code necessary. You just need a bunch of sounds. You can train the model. You can, you know, run our code, and you know, you can see what the AI thinks, or what the artificial model thinks is meaningful in a communication system. So so we're basically using AI, something that is a very new tool, and one that stirs a lot of debates. We're using this tool to really understand or discover new and exciting parallels, and we're discovering that basically now you have this communication system that has the potential to really be informatively complex, right? So in addition to the vowel features that I just presented, the research has long shown that the timing between clicks and the number of clicks matters. And a related paper from SETI showed that timing properties are highly combinatorial as well. And they estimate about 600 classes only on timing, based on timing, possible distinct classes of this communication system. If you add vowels on top of that, you multiply it by 4, 5, 6 conservatively, and you get into a point where each coda can have a lot of information, right? So it can transmit very complex information, and this is where it becomes interesting. Then when you start thinking about, when finding such a complex communication system, what does that mean for for our role in the nature, but also for the way we treat these animals in the legal world. And I believe Cesar Rodriguez Garavito was here a couple of weeks ago and had this really wonderful talk. And I want to present this paper actually because it's very unusual that a linguist and a lawyer and a biologist come together and write a legal paper. But it was absolutely fascinating to write this, because now we have this complex system. What does that mean for their legal world? And Ashley Nemeth is also a co-author, so this is already available. And we really go step by step discussing all the history of language and law and behind them. And I just want to point to a few thoughts that we had in this paper, and you maybe open a discussion of the future. As Cesar pointed out in the previous couple of talks, first it was like animals cannot be sentient. Then it was animals cannot feel pain, and then it was not. The animals are not intelligent. They cannot do complex thought. And Irene Pepperberg, among many other people on this call, I think should prove the opposite. And now it's like language, right? They don't have language, they have rudimentary communication system. No, I mean, with only these couple of papers, we can show that the number of classes the number of information each call can transmit is extremely large. And so we open these questions. This is collaboration with More Than Human Rights Project at NYU Law. And we recently were also covered in the National Geographic, because we think that finding this complex communication system can really change the way we think of their legal status, and can bring maybe even legal personhood to whales at some point. Now, the linguistic argument here is extremely important, I think. And this is first couple of paragraphs. We talk about linguistics and how linguistics can contribute to this debate. We started the talk with the question, what is language? And depending on how you answer this question, the outcomes of your legal thought can be quite different, right? So what is uniquely human? If we find these properties of human language in many animal species, then there are very few aspects of human language that are uniquely human. One of those are, that float around is recursion, and we have another paper where we tested recursion in non-human AI models. But in animals, some people argue there are some papers in birds, but recursion is considered maybe as one thing that humans don't have yet. We have, and non-humans don't have yet, right? So we haven't really found it yet. But if you switch away from this idea that there's a discontinuum, that human language requires some uniquely human properties, into this idea that language arises or is a continuum, and as intelligence or different brain capacities expand, language can emerge, complex communication can emerge. And if you take a position that language, as some neuroscientists are now arguing, among others, F. Fedorenko et al., is that language is not a condition for complex thought, right? That you can have complex thought even without language, which means that language is more of a communication protocol. It's a bridge between my inner state and your inner state. Then basically finding language ability in animals or not finding it is just defining the bridge to their inner thought, right? So you can have complex thought without language, or maybe we just haven't decoded the complex communication protocol that non-humans have, and so that really tears down the barrier that a lot of lawyers and legal tradition has been using to safeguard human rights. And so several design features of human language have already been observed in animals. And we're showing in this work, at least, we're adding a piece into this puzzle that there is this species that has an extremely rich and informative communication protocol that, on some level is on par with language. If you think of how informative our language is, you can think of an average language as having maybe 5,000 lexical items or 10,000 lexical items. So we're not magnitudes away anymore from human communication system. And so one thing that I think also we oftentimes forget is that language needed to evolve, and every complex communication system evolves from simpler communication systems. So when we show that sperm whales have extremely informative communication system, it's important, it's possible that maybe they have not developed yet the fully fledged language, but they're on their way there. So the right of evolution is important, right? So we need to make sure that they have the right to evolve language as humans did, from less complex communication protocols to more complex communication protocols. And even if they do not have, if they don't use all those 3,000 or 2,000 classes yet, they can in principle. And for the longest, scholars thought that human language, the first condition for evolution of human language was development of complex vocalizations. Now, there's that is somewhat disputed topic, but the idea is that we need to preserve their right of evolution to evolve the complex communication system by reducing anthropogenic noise and less interference with their natural environment. So we talk a lot in the paper about noise and the abilities, how it can affect the ability of the offsprings to learn this complex communication system. We know that language is acquired, and for that you need to hear the language. Now, because we discover that spectral properties are important in this communication system, it means that noise interferes with the sperm whales at a completely new level that we were not even looking at, right? So we were primarily, before that, we were primarily interested in the click's presence or absence of a click and their timing. Noise interferes with spectral properties a lot more than with just presence of click. And then so there's a whole new level of regulation that can happen as a result to protect both the ability to communicate, the ability to transmit the culture of whales, and the ability of offsprings to learn the language, crucially, right? Because if you're disrupted, disruption has been shown to interfere with acquisition, even in humans. And we're arguing in the paper that all these new discoveries in science can basically point to new harm that anthropogenic noise is creating for the whales. And so, as maybe as a conclusion, as animal law increasingly embraces non-human animal rights, we can leverage our understanding of cetacean communication to imagine how these scientific advances can result in new legal frameworks. And one of that would be personhood based on several criteria that we have in the paper that that these new discoveries open. Just a final thought: it's very difficult to decode animal communication system, and one thing that is so mind-blowing to me is that oftentimes it requires the animal to learn our human language in order for us to appreciate its intelligence. And this is also part of an argument we have in the paper. So only when Alex was able to master our language to perfection, as Irene Pepperberg has shown, were we able to appreciate that it can count, it can distinguish shapes, compositionally, and so on. And so stepping out of our human bias is a very difficult thing. Similarly with Kanzi and other language-trained animals, dolphins, and so on. Um, um, and so we're very bad at that, and in a sense we haven't done that yet. We have not yet mastered their language to the degree that we could communicate maybe as efficiently as Alex did with us, or other species did with us. So we are in exciting times. We can leverage our understanding of human brain and language and linguistics and all the tools that linguists have presented over the past couple of decades to understand animals. We can use AI to get out of our biases and observe things that we might not have observed without its inputs. And I think we're getting closer and closer to appreciating and discovering that there are species in which learned vocalizations that carry cultural meaning and potentially also non-cultural referential meaning can have extreme rich complex communication that can go into thousands of classes and have the information contact that approximates human language. And I think it's really time to use all these scientific body of knowledge to rethink the way we treat these animals in legal terms. So with that, I think I thank you all for attention, and I'm very happy to answer questions.
Thank you so much, Gašper, for that really compelling and multifaceted talk. There's so many interesting ideas to pick up on in there. And so now is the time, for questions and comments from the audience. So we're going to open the floor up for discussion. A reminder that you can either post your questions in the chat log or raise your hand and I'll call on you. There's already been quite a bit of discussion in the chat already. I've taken down some of those questions, but I'm going to maybe address some of the raised hands here first. And as always, we welcome you to introduce yourself and say a little something about your background before speaking if you'd like. So yeah, Joanne, why don't you get us started?
Thank you so much. Thank you for this wonderful talk. I really appreciate it. I'm a postdoc in the Department of Communication at the University of Colorado Boulder, and I intersect ethology and communication and linguistic studies. And I have a couple questions for you. The first one is, have you used the clicking languages as model to train your models to try to identify potential connections between Codas and human clicking, right? I don't remember how many, it's been a while that I studied this, but Khoisan clicking languages of East Africa. And then my second question is, do we really need to know what whales are saying in order to protect them? I know we want to know, right? Like I also want to know, but when I'm really intrigued about all this legal conversations that are happening, which are so important. And like with your last example about Alex, right? We, as I'm saying in general, right, really like westernized settings, really cared once he really mastered the language. Are we going to get to a point that are we really only going to care if the whales can actually uphold their stands in the court, right? So just wondering your thoughts there.
Yeah, just to answer your clicking question, I think the click is actually a bit of a misnomer in a sense, because it would be better to call them pulses. Acoustically, it would be better to call them pulses, but you know, the tradition is already there and the clicks. So human clicks like those are produced with a suction of air that produces turbulent airflow, and is actually different from the clicks that whales are producing, where they're actually really pulses. And you know, clicks are consonants of human language, just as any other consonant would be. From that respect, I think one has to be. I mean, there's many parallels between humans and non-humans, but there are some also misnomers. When it comes to your second question, you're absolutely right. But the reality is that you know, I don't think we need to understand them in order to protect them, but it is reality that even a great deal of understanding did not lead to enough protection. And so I think we need to use any sort of evidence that we have to make a case um, for their protection. And one of them is, for example, new evidence that there are spectral properties that are highly structured that noise interferes at a whole new level with. And so that's one issue. Um, and yeah, I don't think, I mean, I think you're right, that it should not be a condition, but the reality is that the legal system is not admitting legal personhood to animals yet. And so I think this is, in a sense, it is a next frontier, and we need to make that push. And one of the things that can really help is to show that this protocol that transfers internal states between individuals is in the species highly complex. And if you think of human language, right? If you think of human language, right, we have every all the humanity is based on our language, right? We create our societies around language. We create our law, in a sense, is language. And I always thought, as a linguist, that linguists and lawyers should talk way more, because law is language. And so one of the ways we think about this in the paper is that because language is in such an important aspect of humanity, and such a defining trait of humanity has been for the longest, tearing down these barriers is very important from that perspective, right? Showing that there's complexity, that there's a complex exchange of, you know, that the channel is almost equally complex. I think that can really help with the legal proceedings, and we're working actively on those levels. And so it's not only, by the way, I should say, the sperm whales, we don't know how referential meaning actually works in a great detail, but we have absolutely confirmations of social meaning, right? When I pick up a phone and say hello, you can say a lot of things about my background, gender, socioeconomic background, dialect, where I'm from, right? And they have very similar situations. So their communication system carries a ton of social meaning. They have clans, they have um, um, dialects. And so from that perspective, they're also very close to human society, right? So using language as a social identity marker. And not only that, there is a study from a few years ago, in Shane Garrow from SETI was part of that study as well, where they showed that in areas of the ocean, for example, in Galapagos, where different clans come together more, they amplify the use of the identity markers, which is very similar to, you know, when humans come together, they can amplify their identity by basically amplifying dialectal markers. So there are several parallels in the social meaning as well, and we have a detailed discussion on this in the paper.
Thank you.
Thank you. Francisco, go ahead.
Hey, well, thanks for the great talk. This is my first time in this space. I was wondering if you have thought about how you're gonna like approach how to obtain like referential meaning, I think you called it. What I would understand is what they're talking about, right? And if you think that may be some sort of behavior modification, you know, like training them to do tasks would help in that regard.
Yeah, so that's a great question because there's a lot of cetacean researchers on the call, and they know that better than me. It's very difficult to represent the world of sperm whales, right? So with elephants, I work with Joyce Poole. You have a concept of the tree and a concept of, you know, going somewhere, in the concept of the floor and the sky, and you have all these concepts that we share. There's very little in terms of just representing the world, the meaning, the referential meaning is very difficult because they are so different. The worlds are so different, right? They're how we don't even know. I mean, how do they see and how do they represent? Are they aware of other species? Are they aware of ships? How far? So we're trying to simulate their worlds by actually clicking and seeing what comes back acoustically. So it's very difficult to represent their world, but we're making progress. So you can think of dive profiles. Our tags are equipped with all sorts of measurements, but we're now also thinking actively about representing the ocean, their habitat, with the sound, right? With the sound itself, because they're essentially seeing the sound with the sound, right? And then AI is good for that as well because I saw in chat there's a lot of question about biases. By biases, I don't mean AI is biased in some ways, in the ways that if you train it on bad data, it'll produce bad data. But it is not. It can observe patterns that we humans are not observing, and I think that's part of the reason why animal communication is so difficult, is because you need to observe things at the level that you're not, maybe supposed to because of your biology. And so if you think of, you can build a model that will learn to associate sound with whatever type of representation of world you give it, right? The model couldn't care less if you show it pixels of pictures or if it's showing it some sonar background noise that it gets, right? Or feedback noise that it gets, right? So I think this is we're going in that direction, just like multimodality and interpretability on multimodal models.
Okay, great. Thanks.
I'm going to read a question out from the chat from Nicola, because I think it's sort of, Nicola's got his hand raised next. So if you want to go ahead.
Yes, thanks. Hi, everyone. Thank you for your presentation. It was really brilliant. I am a postdoc at the University of Turin. We have quite same project about semiotics and animal communication. So my question concerns the complexity of animal communication, which extends far beyond acoustic signals like clicks, codas, but includes chemical, vibrational, emotional, for example, in mammals, cues, all deeply embedded in specific ecological and situational contexts. So given that such communication often lacks human-like syntax, how can AI systems meaningfully interpret or even being decode or translate this kind of rich multimodal and ecologically grounded meaning? Thank you.
That's a fabulous question. So first of all, with multimodality, but multimodality is unlimited in a sense. We just need to create better models because currently it's an unsolved problem that we're actually working on. Surprisingly, because AI is so advanced, but it cannot do well sparse multimodality. The reason why sperm whales are so, and cetaceans in general, are so appealing to me as a researcher of vocal communication is that the smell is not there in the ocean, right? They don't smell the ocean. So one modality is already out. They don't see extremely well, at least in the deep. I mean, they see well, but like, the very deep down, the light is not there, so it gets dark. They do not, I've worked with elephants. They do not have as many body parts that they can structurally move, right? I mean, they can move their entire body structurally, and they have the fins. But sperm whales specifically, and they have the jaw. But if you think of like, they do not have a ton of degrees of freedom in the like, for example, complex hands, right, gestures that does not exist like in chimpanzees. So it is in a sense that's while it's so difficult to research sperm whales because their habitat is so different, the promising part and the reason maybe why their communication system is overtly so complex, I was talking in a number of classes, is because probably it is packed more in the acoustic channel than in other animal communication. So you open an excellent question, which is there's multimodality, communication is a complex process. And in a sense, even human communication, I've been like gesturing throughout this talk a ton, and that helps you decode my information a ton. But I think the beauty of sperm whales is that they have less ability to encode complex information in other channels. So I suspect they do that more in the vocal channel.
Wonderful. Sharon, would you like to pose the next question? Maybe I don't know if I've pronounced your name correctly, but the next with their hand up. We can come back to that. Maybe Carrie, do you want to?
Yeah, thank you so much. Gašper, thank you so much for this presentation. My heart is so happy that the conversation has evolved this far. And for me, this discussion about the spectra is really exciting as a way to relate to what we're studying in terms of the sound. My background is I was born aware of my ability to communicate with animals in sentences and concepts and all of that, and just know and be very accurate. But I had no way to talk about that with humans because humans need the vocabulary, and the people around me didn't have vocabulary that would that make sense to them. Carrie the dog is not talking to you, that kind of a thing. And so I have two questions. One is more legal, but I'll start with the intuitive one. I'm curious how researchers, maybe yourself, maybe others, how researchers are exploring their own intuitive, natural, common ground with other species that happens before words as a foundation from which to ask questions relating to everything that our intellect can study and measure, right? How much are we looking to find where we already have that livingness in common, and that informs the way we ask our questions? Because there's the University of Saskatchewan MJ Barrett and her department are studying and finding ways to study intuitive interspecies communication. So there's foundation for that already being established. So it's just the work that I do in the world is helping people recognize that aspect of themselves to be able to have common ground and find that interspecies. I call it the place of no words. So that's one part of the question. And then the other is in the legal sense. This may be really naive, so forgive me, but does our legal language like define an exclusion of rights to non-human creatures?
Yeah, so I'm not a lawyer, but we have a long list. I mean, in general, law has been very exclusive to rights of animals, and the point is that you are not protected in the legal system until you have a voice, right? And the voice is so you need to be represented. And our argument is that it is not enough to have protection from torture. That these are animals, with the complexity of communication and care to other species, to offspring, for example, the ability to care, the ability to mourn the death, or like the fact that they mourn the death, all these traits that we're discovering, and we would discover potentially even more. So the argument is a little bit hypothetical, like what happened if we discovered the ability to get into their internal state and maybe see how they're mourning, how they're expressing harm, expressing pain. That would definitely help their legal case. But the idea is that traditionally the Western law has been very exclusionary to non-human rights. With the idea they cannot bear legal responsibility, and we're exploring how this science can help. So I'm in this primarily from a scientific perspective. So for more information, you'd need to consult with Cesar and animal rights lawyers. But I think what I'm trying to claim is that this very careful discussion of what language is and how it works and how it is and it is not exclusively human, and what that means for their legal status and what a scientist, as a scientist, can contribute to this debate. But for more like detail on the history of law, I think I would defer to Cesar.
Yeah, thank you for that. And I just wanted to drop one other consideration in. I love all of the considerations you're putting in just around human bias, and it's just really lovely hearing how you're looking at all these things. And I just wanted to drop the seed of people are learning our ability to see without our eyes, like to look through blindfolds. And so it to me just speaks to assumptions of what we can study, that there isn't this much light under the surface of the ocean, and so the eyes probably don't work well. But what that doesn't necessarily mean they can't see. And I don't know how we can study all of this. To me, and my heart is with you, behind you 1,000%. And I just love, just keep in mind how much we're capable of, that science can't study. So I know that's probably enough. Thank you. But thank you for everything that you're saying. This has been a beautiful talk.
Thank you so much.
Thank you so much. Sharon?
I'm sorry, I couldn't catch my name just then.
Would you like to pose a question?
Yes.
Yeah, go for it.
My name is Ceren. I'm a psychology student from Middle East Technical University who is mostly focused on comparative psychology. Thank you very much for the lecture, firstly. I want to ask a question from an evolutionary perspective. How can we connect the evolution and formation of language, of human language and of whale language, to the study of their decoding their language? Like, can we use the research on the evolution of their language in decoding them?
Yeah. So I think this is crucial. If I go back, I'm not sure if I'll be able to share again, but can you all see my slides again? Yeah, so I think the crucial thing about evolution of language is this source filter theory of spoken language. So it's a very well-established theory in phonetics, which is we have a source of vocalizations, and then we have the filter of, we filter the frequencies. So it's basically a two-tier system where you have vocal fold vibration, and then you modulate the resonant frequency with the echo with the resonant body. And this is, in a sense, there are two independent tiers that can then create, combinatorial structure. And I'm still developing this, but I think this is a crucial set of conditions that needs to lead to a complex communication system. Although you can have complex communication system with other mechanisms, of course, but I think in human language this was crucial, and in sperm whales it also appears to be, the way they produce these sounds, the codas. And it's very interesting to see, for example, in cetaceans, some cetaceans only have whistles, and some cetaceans have both, and some cetaceans have only clicks. And I think there's a ton of work to be done to really go through each species, understand it, document it, really carefully document it. I mean, again, ocean is acoustically a horrible place, so a lot happens. So there's a lot of distortions. So I think there's just a ton we don't know yet. And but the point is that cetaceans can be a very good evolutionary model, or like parallel to which we can compare humans and our evolution of vocal tract and vocal learning. And there's exciting work, by the way, from a cat biter, and there's other exciting work on chimpanzees, on their complexity of their gestures and the complexity of their combinatorial calls. I think there's just last week there was a paper in Science on combinatorial calls of chimpanzees. So I think in an evolutionary studying, it would be wise to study hominids and cetaceans in a kind of parallel to see how this mechanism evolves, and if it really it allows a more complex combinatorial systems.
Thank you very much.
Harrison, go ahead.
Awesome, thank you guys. Thanks so much for a great talk, Gašper. Super interesting stuff. I was curious if you guys have seen any evidence for like their sperm whales showing like identity through their calls, I guess, because it seems like that's what a signature whistle for dolphins.
That's not, yes, absolutely, and that's not, nothing new in a sense. So Codas, in Dominica, they have a very distinct type of identity Codas. It's the 1+1+3 type, click, 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 click. And if you go to Galapagos, you'll never hear this type. And they have the palindrome, you have a palindrome clan, you have various different clans. But social meaning is extremely well documented, well researched. We're finding out that it appears that vowels are more universal. It appears that sperm whales in Galapagos, while they don't do 1+1+3 codas, they have this both I and A type. This is not published yet, but I'm doing research on the Galapagos. So for sure there's a ton of research that I was not even involved with on the social meaning of those codas. And dialectally, I mean, as a linguist, I love that aspect because they have dialects, they have identity markers, they act social linguistically. So you can literally do social linguistics of sperm whales and other species, of course, as well. But like social linguistics of sperm whales would be a really exciting field.
Thank you for that question, Maisie.
Hi, thank you very much. Thank you, Gaspar, for your great talk. I'm a sociologist of human animal relations at University of Manchester. I have quite a naive question to do with the predictive capacities of AI and the potential abilities of it. So, as I understand it from watching other talks, one of the things that surprised the community is that the machine learning programs are able, through their kind of predictive capacities of understanding how a conversation evolves and so on, to communicate, to theoretically at least communicate with the animals under study before the humans know what that machine learning program is saying. So I guess that has implications for playback experiments, some of the playback experiments that you were talking about, in terms of the kind of conversations that could be taking place and in terms of the ways that that could potentially kind of evade human control.
Yeah.
Can you speak to that? Is that right? Have I understood that correctly? And can you tell me about how much control you have over that and what ethical and legal issues that might raise?
Absolutely, and this is precisely what we address in the paper, in the legal paper. The problem with that approach. So the approach I presented that we call CDEV is the following: you have a model that you understand well, you show that it learned stuff on humans, you train it on animals, and then you use your ability to understand the model to understand what is meaningful in animals. What another approach is you create a chatbot that learns to continue animal sounds of animals, right? You give the model some animal sounds and it'll continue, and you don't know anything what it does. You have no idea what it says, as it's continuing. It's basically like a chatbot, right? Every chatbot predicts the next word, and ask it a question, it'll predict next word until it gives you a good answer. So what we claim in the legal paper is that this is actually an approach to be avoided, because until you understand AI, what the AI is doing is difficult to minimize risk in research. So it's better to avoid this idea, this kind of research, the approach where you're playing back something you don't understand because you don't know what the reaction that might evoke in animals. You don't know what the model is doing. You don't know what the outcome is. So with too many unknowns, it's difficult to um, minimize risk. And minimizing risk is, of course, one of the guiding principles of animal research. And actually, SETI with MOTH, the Modern Human Rights Project, is creating guardrails for doing AI-assisted animal research. And part of it will appear soon, but part of it is already in the legal paper. And we hope that serves as a kind of a document to which law and regulation can look back as in a sort of a white paper. But yeah, so I think we're taking a slightly different approach, and I would in a sense, before we understand really well what your model is doing, I think it would be wise to avoid this kind of playback experiment. That being said, you don't need to. SETI has actually, there's a theory group at SETI that shows that you maybe don't even need to do playback experiments. And we didn't do any playback with our model, yet it suggested us to look for spectral, for example, and suggested spectral properties to be meaningful. In other words, you can use AI to the benefit of understanding animals without doing the actual playback experiments.
Okay, thank you.
Thank you. We have a lot of questions in the chat. I'm going to just address them in order. Some of them have already been discussed in the Q&A, but I think the first one was from Irene. She asked, how is the program semantically grounded? I think this is in reference to the baby LLM learner, but I'm not completely sure. I don't know if Irene's still on the call, if she wants to speak to that in more detail.
I can
Irene had to leave, guys. So, but she can always watch the recording, you know. But yeah, she.
I think that's Irene was the person that I started the animals, so it's animal research with, and I'm very honored that she's in this. She was in the call. It's not really semantically grounded yet, but we're for the initial purpose there. I mean, it's not grounded in the external world. For the initial purpose, that was enough because we only wanted to understand what the meaningful building parts of this communication are, and we were not yet interested in referential meaning. And now, as you know, was already discussed, now that we're interested in referential meaning, we're adding multimodality to the model. But for this initial, when the question is, what are the meaningful moving pieces of this communication system, you don't actually even need the referential grounding, and that's the beauty of AI. Just like our AI model learned words without actually being connected to the world in the visual sense. So from that perspective, it can be also an advantage, but of course it's a disadvantage if you want to understand the referential meaning of this communication system.
We have another question from Sinan in the chat related to grounding. Sinan asks, are there any efforts to ground Codas on observable behaviors using either manual or AI video analysis? And if so, how to make sure that large language model behavior annotations don't carry anthropocentric biases in the data labeling process?
Right, we're not using LLMs to do data labeling, and I think there is progress, but unfortunately the work is not published yet. So we're making progress on the multimodality part and getting aspects of meaning, potential referential meaning even for vowels and codas. But I guess that'll be presented at one of the next talks, but it's not published yet. So
Carolina asks, have you seen any bias on the vowel usage depending on the sex of the sender or the social context that the sender was in?
There are some interesting biases in vowel usage in general. We have not, well, the thing is that these are matrilineal societies and vocalizations are exclusively by females. Males are more or less go silent after they leave the society. But there are so many interesting aspects that this spectral properties open, like how does this get acquired, how the babies, which type gets acquired first, how the babies produce them. It was basically all the unknowns that we still have to answer. But there are some interesting distributional patterns that we're describing right now that are really meaningful for the research.
Okay, and Emma asks, how large and diverse are the data sets being used to study sperm whale communication? And does it contain enough spatial diversity to notice whether or not the distributions vary across the Earth, either as a result of communication about the local region or because of the potential regional dialectic differences?
Yeah, that's a great question. So I again, a part of research that we haven't published yet, but should be at least as a preprint soon, is that Galapagos, for example, populations have very similar distributions in terms of vowels as Dominica whales. In terms of sizes, actually it's very difficult to do research on sperm whales because they dive so deep and they need the open ocean. We are developing, the SETI is developing drones that will, minimally invasively let the tags on the whales. We also have gliders that are basically silently following and recording whales, which is not disturbing them. And so we're collecting data, but it is a very heavy undertaking because the ocean is not, in a sense, is a difficult place to navigate in research. And I see Diana is nodding. I mean, I think on one level, it's better to get it's small amounts of very high quality data. That's why I think having tag data is important than massive amounts of non-qualitative data, quality data. But we're also innovating in a way that this kind of research is done and the whales are recorded. And there's lots of research on bio-inspired suction cups that you can use for tags and how to do how to retrieve information and data from the tags, and use the latest in AI vision to tag the whales. But yeah, I think there's always a trade-off between quality and quantities. So I think even smaller amounts are okay if the data is high quality.
There's quite a bit of discussion, or there's sort of a long thread in the chat about things like human bias, machine learning biases or limitations. So some of the specific questions or remarks had to do with, whether statistical analysis of large corpuses of data can tell us anything about meaning. What are the sort of implications of the differences between human neurons and artificial neurons for the kind of knowledge that we can ascertain from AI models about biological cognition? And this kind of touches on something I was curious about, because obviously in your work, you allude to the symmetries between animals, humans, and computational machines, specifically in the realm of language and learning. And, maybe this is too philosophical of a question, but I'm curious if you think that these shared regularities tell us something about, say, the effectiveness of your models for explaining and predicting phenomena, or if you think that there's something sort of deeper underpinning these symmetries. Sort of, in other words, are you kind of like a realist about these convergences in the data or in your findings, whether they're reflective of a true or a close approximation of some kind of true account of a shared reality of organismal and machine cognition or communication? So
yeah, so that's an excellent question. I mean, on some level you can be agnostic as long as your model is giving you nice information. You can be agnostic, but I think there is value to building realistic models of human language in the true sense, right? And I take this seriously. So when we build models, we even we use them CNNs, which are better approximations to human neurons than, say, a transformer is. We're in the model we have virtual mouth. So basically, our model generates movement of tongue and lips and EMMA recordings to generate sound. So we really, we do want to approximate the reality. And I think this concept is important. Language as informative imitation, right? I mean, I think that's a powerful concept. And if you think of language as informative imitation, then you can build model around that, and then you can see, are there neural parallels? And I do think at some level, I want, I strive to be realistic. I want this model to approximate humans. And if you think of it, like our brains are in a sense very similar to that of sperm whales, right? I mean, they have larger areas for audio processing, right? Because the audio is so important for them. But it's a biological neurocomputation that needs to informatively learn. And if you can do a mathematical approximation of that, if you can train a neural network with relatively similar processes, I think that is valuable and can tell you how things emerge. You can do all sorts of simulations, right? You can do experiments that you would otherwise not be allowed to do for ethical reasons. So I think there's value in that. And of course, the general disclaimer applies, right? Every model is wrong, but some are useful. And even if you think that none of this is even remotely similar to what we do, the model is still proven to be useful. At least it was useful in our case when we were trying to find out what is a meaningful, aspect of this communication system.
Great, thank you for that. Francisco, do you want to?
Yeah, thank you. I'm wondering, with the information that you have now and how difficult it is to get labeled data with cetaceans, if you think it would be possible to do an experiment like this with a simpler animal that is more accessible in order to guide like the future of the research on this bigger project.
I think the more animals we are able to non-invasively listen to, the better. I think there's so many species that we have very little knowledge, very little quality recordings. I'm very interested in sperm whales because, from my selfish perspective, I have not seen anything like that. From my, I'm a phonologist. Phonologically, they have very exciting things, but there are a ton of other, species, and I think the exciting thing is I think I sense some renewed excitement about doing this kind of work and just like putting in time and going to the field and recording animals. But I have learned, I mean, I'm new to this field of cetaceans, but there's so many species that when I try to dig out information, how their communication system works, if there is any available data, there's so little known that I think there's a lot of work to be done.
Okay, just a follow-up on that. What's the minimum amount? I'm sorry about the noise. What's the minimum amount of data that you consider like usable in order to do something like what you are doing with another type of animal?
Well, we were able to pretty certainly establish this clear pattern of coda vowels based on 3,000 codas from, 12 whales in the time span of 2 years or 3 years. So if you have quality data, I don't think, and in a sense, this is a very simple pattern. I mean, it's exciting. It's exciting precisely because it's so simple. It's not some complex combination of elements. It's just a simple, discrete pattern. And I think that made it easier to be discovered based on small data, relatively small data. But I see value in discovering simple patterns because that's what human language in many ways is as well. So I don't think I don't think you need, I mean, for other more complex stuff, for sure you need more data, but for simpler things, I think even with smaller amounts of data, with the with the know-how what to look for. That's the important thing, right? You need to know what to look for and analyze it from different angles. I think it's fine. And I think I'm a big proponent. So I started as a historical philologist, and that meant I had to learn dead languages. And those of you who studied dead languages know that they're very difficult, and you need to study them hours and hours and just read the text before you get what they mean. And I think I'm a big fan of doing research by just actually looking at data for hours. And after we trained our models and it suggested something, it took hours and hours of looking at data before this, even simple pattern was, we were able, I was able to see, wow, this is like this part of spectrum has this recurrent properties across whales. So just spending time with data, I think, is super important.
Okay, just the last thing. You found that visually, like you were looking at the data and you identified that pattern by yourself, or it was like the algorithm that told you like,
No,
hey,
no, it was at that point, algorithm just said spectrum is meaningful. It didn't says there are two types. It didn't say there are diphthongs. That was done based on spectrogram analysis, and actually in a program that linguists use for vowel, and speech analysis.
hey, that's cool. Thanks.
Diana, thanks for joining us. Do you want to hop on the call?
Yeah, hi. I'm sorry. It's very noisy where I am, so I keep on putting my hand down. First of all, Gašper, thank you so much for such a deeply moving and detailed description of the work. And I just want to thank you from probably all of us also for your thoughtfulness about the ethical aspects. I know it's been an ongoing conversation. Many of us have been involved in with you. I think that also, I just wanted to say a couple of things quickly. I think that when we talk about language, it's real from a philosophical point of view, it's been the great separator of us, as you've said, from the rest of the animal world. If you go back looking at historical accounts of how we've thought about ourselves with other animals, it really has been us versus them. So I think this is a terribly important conversation, and I'm speaking with my trustee hat on as one of the Interspecies Internet trustees. This talk really has exemplified what we've tried to do, is bringing in a forum of discussion here where we think about both intraspecies, as you're doing, looking at how the species are communicating and trying our best to decode, and then interspecies, like people with Irene Pepperberg, the folks who've done the exquisite ape work, some of my work and other people's work with dolphins, trying to give them artificial codes, because we haven't been able to understand. And I think it's that marriage of what we're learning from them with artificial codes, that they are thinkers, and then looking into their own communication system, that I think gives me hope that we'll be able to convince others that these are thinking animals. I mean, I think we know that they think now. It used to be, can they think? Now we know they think, but none of it seems to be quite enough. And I'm just really excited about the work that SETI's doing. And I thank you for thinking about both the science and the ethics. I just wanted to say that.
Yeah, thanks so much. I mean, to me, it was so exciting to be prompted to collaborate on this legal paper, because it made me think about, what is language? What if the language is just a channel that I need to use to see inside them, but complex thought is just a separate thing. And exciting work in neuroscience by Ev Fedorenko actually, points in this direction. And then just clarifying these things, and of course I think we have to be objective in the sense that we are in this paper we list all the potential views on language, right? And what does mean if X, and what does mean if Y. But I think it's just I'm fascinating just how difficult this undertaking is. I mean, I'm joking. We know we have split that we have a CERN protons. We're shooting protons into each other, And we're so at the basic level with animal communication and their understanding their inner lives. And, not to say there have been huge advances in dolphins, bonobos, all these species, but in a sense, for many species, we're still at the very, very beginning. And it's such a difficult question. And like thinking about this for this paper has been, to me as linguist, really transformative, because now I think of these big picture questions, and before I didn't even maybe think about.
Yeah, and I just want to say that I think that with the kinds of tools we have now and the advances in using them and talks like this and sharing it, again, in our forum, we hope others will gain a great deal in their own work and really be able to make these collaborations, whether it's, with other species as well, but learning what's capable. So I'm hoping we'll hear a lot more in the future. We're really excited about this. Thanks so much. Yeah.
And just to add one thing, I think the linguistics as a field is moving in the right direction as well. I'm very happy that this phonology talk, the talk about whale phonology, was actually accepted as a presentation in the main phonological conference and linguistics side as well. And I think it goes both ways. I think linguists can offer a lot of tools, a lot of methodologies, a lot of tools to the biologists, to the animal communication systems, and vice versa. I think linguists are finally, many, I think of us are opening up to animals, because there was traditionally such a divide between biologists and linguists, and there was some sort of care, caution in doing this. But I think with collaborations and with these new tools, and also with old tools, not just new tools, right, but the tools that were overlooked because we didn't talk to each other, I think it's exciting that's changing.
Thanks.
Thank you so much. I think that's about all the time we have today, but thank you, Diana, for those thoughtful closing remarks on the sort of scientific, ethical, and philosophical consideration of non-human minds. This sort of effort to break down the barriers between humans and the rest of the living world and challenge our sense of exceptionality. I'm really tempted, Gašper, to ask you to elaborate on your recently published work on linguistic recursion in AI, but I probably best left for a later talk. But thank you once again for such a stimulating presentation and discussion. The work that you're doing with Project SETI and with Cesar and More Than Human Rights is just so important to the field. So thank you, and we can't wait to see what's next. If you'd like to learn more about Gašper's work, please check out his personal website, which I'm about to share in the chat. Here we go. The landing page has links to all the places that you can find his work online. The only one that was missing is his TikTok, so I added it here. I don't know if you're still active on that platform, but yeah, so check out the work there. And yeah, and I'd like to also, thank the Interspecies Internet community, as always, for engagement and your interest in our monthly Interspecies Conversations lecture series. If you'd like to learn more about our organization, stay up to date with our lecture schedule and other events, projects, and activities, if you want to donate to help fund our programming or connect with a community of researchers and enthusiasts, then please follow us on social media. Visit our YouTube channel, join our Slack, subscribe to our newsletter. Carolina should post these links in the chat, so check them out. Yeah, so on behalf of Interspecies Internet, the trustees and the community, thank you, Gašper, once again for joining us today. And we hope to see everyone again next month for another Interspecies Conversations event. Have a wonderful weekend, everyone.
Thanks so much, everyone.